Welcome, everyone. Today, we're diving into a concept that underpins all engineering measurements, yet is often misunderstood, and it is uncertainty in electrical measurements. Let me begin with a fundamental truth from physics. No measurement is exact. Whether we're measuring voltage, current, resistance, or power, every quantity we record is an estimate. And it's our professional duty to quantify how good that estimate is. So let's unpack what uncertainty means, not just as a number, but as a consequence of natural variability, instrument limitations, and even our knowledge structure. At the most fundamental level, uncertainty arises from microscopic thermal motion of electrons, which affects voltage and current readings. Quantum limits of charge measurement, which is single electron fluctuations. Entropy in statistical mechanics, which means any physical quantity at equilibrium fluctuates within a probability distribution. Electromagnetic noise, which cannot be entirely shielded. Thus, uncertainty is not just a flaw in instrumentation, it's a law of nature. Let's define three precise terms used in metrology. Measurement is the process of assigning a value to a physical quantity. Error is defined as the difference between the measured value and the true value, which we never actually know. And finally, uncertainty is a quantified estimate of how much doubt we have in our measurement. Uncertainty is not error. Uncertainty tells us that if we repeat the same measurement many times, how much variation should we expect? We divide sources of uncertainty into two categories. First category is systematic errors, which are predictable, like having constant bias measurements in the same direction, which is caused by imperfect calibration, thermal drift, offset voltages, etc. For example, a voltmeter that always reads 0.02 V higher due to internal reference error. Second source is random errors, which are unpredictable. They vary from one measurement to the next, and they are caused by thermal noise, contact resistance fluctuation, analog to digital quantization, etc. For example, fluctuating current readings from a Hall effect sensor under environmental noise. Beside the categories of uncertainty sources, metrologists define uncertainty using the guide to the expression of uncertainty in measurement. We have type A uncertainty, which is evaluated using statistics and requires multiple measurements. For example, taking 10 voltage readings and calculating the standard deviation. We also can have type B uncertainty, which is based on non-statistical sources, like manufacturer specs, instrument resolution, previous calibration reports, and engineer's judgment. Here's the general method for calculating type A uncertainty. If we take n repeated measurements, we will have set of results as x1, x2, all the way to xn. We can compute the mean by adding those measurements together and divide the result by the number of measurements. We also can compute the standard deviation. For that, we need to calculate the distance of each measurements from the mean and then add square of all the distances together. Then we divide that by n minus 1, where n is the number of measurements. And at the final step, we take the square root of the result. Quick detour. Why in mean we divide by n, but in the standard deviation we divide by n minus 1? The answer is in probability and statistic. One of the fundamental rules is that all the data in our set should be independent. In calculating the mean, we have an independent measurements, but in the standard deviation, since we already know the mean value on of the measurements become dependent, meaning we can find the last measurement as function of other. So we lose 1 degree of freedom. The standard uncertainty also can be calculated by dividing the standard deviation to square root on n. This quantifies how repeatable your measurements are. Let's walk through a practical example of how to calculate measurement uncertainty using a digital multimeter. Imagine this situation. You're measuring the resistance of a resistor using a handheld digital multimeter. The display reads 99.6 ohms and the resolution of the meter is 0.1 ohms. This means the last digit you see can go up or down in steps of 0.1 ohms. We begin with type A uncertainty, which is based on statistical variation. Here are the steps. First, we calculate the mean value. In this case, it is equal to 99.58 ohm. Next, we calculate the sample standard deviation, which measures how much your readings deviate from the average, which is equal to 0.0836 ohm. Finally, to get the standard uncertainty of the mean, divide the standard deviation by the square root of the number of measurements. By doing that, we will have the standard uncertainty equal to 0.374 ohm. This value reflects how much uncertainty is present due to random variations in repeated measurements. Now let's calculate the type B uncertainty, which arises from the instrument itself. Here, the multimeter resolution is 0.1 ohm. This means the smallest change it can detect is plus and minus 0.05 ohms, which is half of the least significant digit. We assume that any true value within that range is equally probable, which gives us a rectangular distribution. To find the standard uncertainty for this case, our type B uncertainty is 0.0289 ohm. You might ask that where the square root of 3 came from. The square root of 3 in type B uncertainty comes from the standard deviation of a uniform or rectangular probability distribution, which is typically used when you have a bounded range of possible error, but you have no reason to believe any value is more likely than another. This is a common assumption when you only know the resolution of the instrument or a manufacturer gives a maximum deviation without giving a distribution type. So even if your measurements didn't fluctuate at all, the display resolution alone introduces an irreducible layer of uncertainty. Next, we combine the type A and type B uncertainties. Because these two are independent sources of uncertainty, we combine them using the root sum of squares method. Therefore, our combined uncertainty is equal to 0.0473 ohm. We are not done yet. To report our measurement with higher statistical confidence, we introduce the concept of expanded uncertainty, denoted as U. The standard uncertainty we calculated earlier, approximately 0.047 ohms, only gives us a 68% confidence interval, meaning the true resistance value lies within plus and minus 0.047 ohms of our mean with about 68% certainty. However, in engineering practice, we typically want to report results with 95% confidence, which corresponds to about 2 standard deviations from the mean in a normal distribution. This is where the coverage factor K comes in. For 95% confidence, we use K equal to 2. We multiply the combined standard uncertainty by this factor to compute the expanded uncertainty. So we have U equal to 0.095, or we can say around 0.1 ohm. Thus, we report the final result as equal to 99.58 ohm plus or minus 0.1 ohm and state explicitly that this is with 95% confidence. This communicates not just the measured value, but also how certain we are about its accuracy. Let's recap. You took 5 readings to assess random variation type A uncertainty. You analyzed the instrument's display limits type B uncertainty. You combined both statistically. Then you scaled the result to a 95% confidence level. This entire process allows you to say not just what your measurement is, but also how sure you are about it. That is the difference between guessing and engineering. When formal specs are unavailable, honest engineering judgment becomes paramount. You must disclose your assumptions, clearly state the model, like if it is uniform, triangular, or normal distribution. Avoid overclaiming precision, because engineering without uncertainty quantification is guesswork. Final takeaways. Uncertainty is not error. It's the quantified doubt in any measurement. It arises from both random and systematic effects. Type A uncertainty is statistical and type B uncertainty is knowledge-based. Uncertainty can be estimated responsibly even without manufacturer data. Mastering uncertainty empowers your measurement credibility.